last lecture, we discussed this idea of thermal activation. That is that the kinetics, which is the set of relevant time scales associated with moving around configuration space, in an energy surface, energy landscape that contains barriers and basins, is characterized by very slow relaxation processes associated with a mean first passage time through this point, which is exponentially long, and relatively fast oscillation processes, which is a characteristic time scales through which systems locally attains local equilibrium within each basin. And this is the key to understand a huge variety of processes. Enzymes are basically nanomachines to lower activation barriers. If you think about it, they make reactions possible by lowering the activation barriers of reactions. Catalyzers in general, anything that lowers an activation barrier. So typically the way nature works and biomolecules operate is through activation barriers. Because activation barriers are extremely convenient ways to switch on and switch off processes. Think about, you have a process that involves some cellular cycle or some cellular function and is carried out by some protein. And for example, this protein needs to carry on a conformational transition to become active. Well, you might imagine two ways. One is which anytime you need that protein, you produce more of them, right? Or, and that will proliferate the number, the biological function by the time scales, that is the time of synthesis of all the proteins you need to synthesize. Or you can throw around a few enzymes that walk around and lower activation barriers for the protein to become in an active state. Now, the same enzyme can carry out many catalysis, many activations, interact with many proteins. And all of a sudden, a number of proteins rapidly become available for performing activity. If the state above the barrier, after the barrier is the active state. Right? So you see how convenient it is to have these barriers from an evolutionary perspective. Because basically once you have a barrier, you can stop and activate and deactivate process very, very efficiently. Okay? So this example, on the one hand, tells us basically the most important aspect of whatever happens out of equilibrium in biological systems at a macromolecular level. At the same time, it draws our attention towards what is the most significant challenge that in 2026 we still have to face to simulate this process. Because you see, even if we have a very good model for the atomic forces that carefully represents the Bohr-Oppenheimer surface, remember that, right? Well, if we want to use molecular dynamics or Langevin dynamics to simulate the dynamics and understand all of these complex kinetics, we have to simulate exponentially long activation times. So we need to be prepared to simulate molecular dynamics for exponentially long time intervals. Now remember that we also at the same time have the problem that with the hard cores and fast vibrational modes in macromolecules, which means that we need to take extremely small integration time steps, you immediately come to the conclusion that very often you need to simulate for 10 to the 12, 10 to the 15 time steps. Gigantic number of time steps. Making, in fact, molecular simulations for most processes of biological interest relatively useless unless we learn how to deal with this problem. So this is the heart of what is called a rare event problem. Reaching equilibrium or even crossing a single barrier can take exponentially long time. And so if your mindset is that of an initial state pushed forward in time by integrating many times independent molecular dynamics trajectories, each of them will contain a successful event for times that are exponentially long, to a point that you rapidly grow into paradoxes. Let me, not paradoxes, but let me give you an idea of how bad this is. Okay? Say, what is a typical folding time for a protein? Do you know? Let's discuss single domain globular protein. Of course, if you're talking about multi-domain or quaternary structures, things get even more complicated, or chaperone-assisted proteins. But let's think about, say, refolding of 100 amino acid protein, maybe 200 amino acid protein, right? Well, there are ways to correlate the rates to the architecture of the fold, but let's not go into those details. I would say the minimum time scales that you encounter is the milliseconds. But this is really for particularly fast folding globular proteins. Well, the most typical protein I know is canine lysozyme. Why do I take canine lysozyme? Because it's been crystallized in all possible ways, because it's a very soluble protein. People have to deal with it. So I consider it an easy protein. It's experimental. Well, canine lysozyme, if I remember well, has a folding time in the second time scale. Okay, or hundreds of milliseconds at least. Might be wrong by a factor 10, but not so much. So, second, I can go on. I studied a system of proteins once who folded in 60 minutes. Now, this is a bit of an outlier, to be honest. Because some proteins even have a life turnover in the cell that is shorter than that. So it really depends on the system, right? But certainly milliseconds about. If you cannot simulate a millisecond, you have no access to anything interesting. And if you cannot arrive to the millisecond, you're barely scratching the beginning of what I call the biozone. Because this does not only concern protein folding, it concerns also misfolding, it concerns allosteric transitions in many cases, complex ones at least. It concerns typical processes that are involved in proteins performing non-equilibrium walking around the cells and all. So all really interesting conformational transitions in biophysics occur in a biozone that ranges for a few milliseconds to the infinite and beyond. But say, I would say the minute is a fairly good breaking point. If that you're lost. So where do conventional supercomputer stand in this plot? So how long can you simulate with a fairly decent GPU farm today? Say you buy time on Leonardo, Italian's largest and one of the Europeans' largest computing infrastructures. Well, I would say that if you have a lot of money, and I mean in the order of hundreds of thousands of euros, right? You can probably collect a statistically significant fraction of trajectories that are in the few tens, maybe 100 microseconds if you really spend a lot of money, and maybe 5 months of calculations. Okay? So even, and what about your GPU farm that you have in Bicocca? We don't have one at the moment, but just to give you an idea, right? The one that I have a few GPUs that I use for my local small project that I was allowed to use from Sibilla when they dismissed some of their computing facilities. And with them, maybe you can get 1 or 2 microseconds. So we are a factor 10 to the 3, maybe 10 to the 2, 100 times away. If you really are super expensive, you are 10 times short of seeing a single folding event for the simplest possible fault. And we understood from statistical physics that single folding event is not going to take you very far, right? Because we need a statistically significant collections of events, right? So clearly, playing molecular dynamics doesn't take you far. You can use it for possibly other things. I don't know, watching how a side chain of a protein probably rearranges in a given situation. That's probably, or how secondary structures may form and dismount locally. This is probably a problem where you can use molecular dynamics for. But certainly not understanding major rare events, okay? Which is where the juice of a problem is, as a matter of fact. So because of this extremely, I didn't finish the landscape. Now in 2010, DE Shaw Research published the first protein folding simulations of mini proteins. So these were 12, if I recall well, subdomains of proteins, or specifically single domain proteins that are not biologically relevant, typically are subdomains of larger proteins, that have protein-like properties. They have a unique state, they have cooperative folding into unique states, and for which the crystal was known. And they all were selected and designed, in one case even designed, to have sub-milliseconds folding time, typically in the few tens of microseconds, several hundreds of microseconds at the most. And they did that because with this, they had designed a supercomputer called the Anton supercomputer that where all the major codes, all the major algorithms for solving molecular dynamics were engineered in hardware, not compiled and coded. So this typically yields an acceleration function of 10 to the 3, maybe 10 to the 3 relative to GPUs. At the time, GPUs were not available in 2010. So by this computer, they were able to access the milliseconds time scale, which allowed them to see that, in fact, the force fields they were using were able to see folding and refolding in equilibrium of many of these proteins because they were for the microcycles timescales, tens of microcycles timescales. Okay? So the force field had enough physics encoded into it, or enough chemistry or physics, whatever you want to call it, to recognize native states by molecular dynamics, which this was a gigantic achievement because until that moment, people didn't really know whether the uncertainty of the force field was making all this a lost cause to begin with. Maybe there was no way to come up with a model of force field which was sufficiently accurate for MD simulations to make sense. Right? So this was, from a conceptual point of view, a gigantic step forward. From the practical point of view, not quite so much. And in fact, I believe what Anton makes is what the Show Research, which is a private company, for business company, for profit. They make their profit by cooperating with pharma on whatever binding problem or whatever thing they, not on simulating protein. This was a proof of concept that demonstrated the power of this. But it doesn't scratch the biosome. So it's not a, now Anton is in the third generation. It has gone up by a couple of factors, 2, 3, maybe 4. I don't quite remember. It could be even 10. I'm not sure. But even if you go to the 10 milliseconds and you increase by 2 the number of atoms you can simulate, or 4, you're still so far off from the biosome that it is clear there is not the next generation of supercomputer that's going to take us into the biosome. It's most likely the next generation of ideas and computational technologies. So this has driven people for a very long time now, for the good part of 3 decades almost, to develop ways to come across the rare event problem. And these ways, they go under the name of enhanced sampling methods. Now, there are gazillions of them, and many of them are variants of the same idea, even though the inventors didn't copy each other. They look different maybe in the surface, but then if you boil them down, you can map one into another, basically. Not all of them, but this is to say that when I was beginning to do biophysics, say in the mid-10s, 2000, 2010, 2011, 15, there were conferences constantly on new of these methods. Now this production has slowed down significantly. It has turned more into an AI and machine learning for molecular simulations, as we shall see. But I want to give you an overview of what enhanced sampling methods basically are and how can you make sense of the zoo of enhanced sampling methods that there is. Okay? I would say enhanced sampling methods divide into 2 classes. Up here I would call the exact, and I would put commas, because none of them is really exact. What I really by exact is less wrong, or less approximate, but I will elaborate on what do I mean by that. And here I would call them approximate and again I put commas. I want to start by doing this and then elaborate what do I mean by these two words. The first distinction is method that in principle don't add any additional artificial physics information into the system, right? But basically find clever ways to exploit whatever there is. Okay? So I will quote a few names and then maybe go over the most important of them, right? One of them is replica, exchange, molecular dynamics. RAND. I might forget someone, and I hope people who will listen to this lecture don't take this the wrong way. There are so many that this is just a subset that illustrate differences rather than a comprehensive set of enhanced sampling methods. Okay? Replicate exchange molecular dynamics is certainly one of them. I will put in the list transition path sampling, although this is kind of a borderline. For reasons that when I discuss, because transition path sampling still needs the definition of a reactant and a product, which is something you have to provide the system. And then a third, again, going down to some extent into from more exact to less exact, meaning that you have to rely on assumptions. There are Markov state models. And here, probably you're familiar with the word folding at home, which really pioneered with Vijay Pandam in his group, these ideas. I will quickly discuss this, maybe transition path sampling a little bit later. But all of these methods, plus possibly a few more, if somebody comes across with it, they basically take in input nothing. Well, this is not exactly true, but they don't alter the dynamics artificially. They don't push you through the barrier and then hope that whatever you see makes sense. They use the physics information that is already available. Again, to some extent, you see, to be fairly rigorous, transition path sampling does use some information. Microstate model is variationally using some information. But as a general scheme, I think it's fair to say. Because what I mean by approximate, I mean you really need to tell the system something you have no idea about and rely on this physicochemical intuition of which you have to put on top of a simulation to accelerate. So basically, the approximate are based on doing physics or chemistry. I really don't understand the distinction at this level. If not by the fact that I have a PhD in physics, I have very, very little understanding of chemistry or no understanding of chemistry whatsoever. But that's my problem. In general, people call physicochemical intuition. Intuition. Then you put into an algorithm and you get prediction. Clearly, if the physical chemical prediction you put into the algorithm is garbage, what you get is garbage. Garbage in, garbage out. But what is the physical chemical intuition we are talking about? Most likely, this is in the form of so-called collective variables, CVARs. This is a name that is very popular in this simulation community, so I encourage you to familiarize with what it means. Collective variables, CVARs. So for instance, collective variables are heuristic function of the atoms which in some way encode the information about the slowest processes in the system. Let me give you an example. Say a collective variable in protein folding could be the fraction of native contacts. How many contacts that are in the native states are actually formed in a given protein state? Okay? For instance, you have a completely denatured protein. The fraction of native content is 0. None of the native contacts is formed. You have a fully formed protein. The fraction of native contact is 1. Right? Now, clearly, proteins work by essentially forming slowly these contacts and disrupting, and then all of a sudden these contacts are formed, and at some point sufficiently many contacts are formed that you climb the barrier. Okay? This is much faster than the motion of the atoms. This is much faster than the formation of or the rotation of side chains of amino acids, and so on and so forth. Okay, so the dynamics of collective variables have to obey a number of properties. The collective variables are slow processes, and they are order parameters. What do we mean by order parameters? They must carry information about transitions I'm interested in. For instance, fraction of native contact can distinguish from a native state in which all contacts are formed, where it is equal to, say, 0.9. There's always a residual part of proteins that by entropy reason remains unstructured. And a denatured state where, say, it's equal to 0.2. Maybe because locally some contacts are formed in the beginning of an helix somewhere in equilibrium, right? So you must be able to distinguish two valleys by two different values of the order parameter. And ideally, you should have all the collective variables that represent all the slow processes so that the dynamics in the perpendicular plane to the collective variable is much faster. Within the same adiabatic idea of the Born-Oppenheimer approximation, where the electrons were faster and then going to the ground state, you want to copy that and say, okay, I have these 3n coordinates, but I can arrange them into a subset of coordinates called collective variables. Let's call it xi1, xi2, xin, which are the complete set of slow functions that are really important for the transition. Everything else is so much faster that it's considered to be in equilibrium. Okay? What are the collective variables? Well, at this level, we have no idea. We have to resort on chemical-physical intuition. But if you make a guess, you can feed this guess into the algorithm and maybe let the algorithm accelerate the dynamics only of the slow dynamics. For example, by coupling the slow coordinates to a larger temperature, or by doing other things that we shall say. Okay? The result is, of course, a theory that has nothing to do with the original dynamics. Now, in some cases, and I am aware of two of them, one of which I was involved, and one of which was done by the group of Parinello, Laio, Bussi, and companies called metadynamics, you might have heard of. You can even prove that if for an ideal choice of collective variables, where idea systematize this concept that I gave you in a colloquial way, for ideal choice of collective variables, the algorithm will give you the ideal sampling. So at least you know that if you're very good in choosing the collective variable, you get something that makes a lot of sense. But nobody tells you that you're actually good in getting the collective variable. And I'm not going to tell you this algorithm now. We'll probably see some of them later. So rather than approximate, I want to give a new name that is CV dependent. Collective variable CV is dependent methods are methods that accelerate the dynamics by taking an input information you give for granted about the system, or you hope you know. Okay? Instead of exact, which is a bad word, and so I can take away the commas and the bad words, I contrast to CV dependent, CVs free methods. So methods that don't require any input from the user in terms of I know a little bit about something about this reaction. This is the slowest process that has to occur, so I parameterize that process into a function, a collective variable, and then I try to push this function in such a way that it accelerates the dynamics. Okay? Now, in these methods, people do not do that. So why ever choosing these over this? I mean, this will win every day of the year, right? If you have something that doesn't rely on any assumption on collective variables, why should I go for methods that need collective variables? Any idea? Absolutely. Because there's so much you can do with collective free variables. They push forward, as we shall see. They push forward, but they still are very expensive for many cases of interest. So, while this method have proven extraordinarily useful for problems that are at the border of the biozone, hereby extending the regime of processes you can actually study. So they played an enormous role in showing that you can use simulations. There have been success stories of those. They're not the ultimate solution. You're still order of magnitudes away and they all fail more or less in similar ways. Now, we'll discuss some of them and how they fail. On the contrary, CV dependence can really push you into the biozone. For instance, I will show you a movie of our CV dependent approach of co-translational folding simulations. You see a protein folding with all atomistic detail in the ribosome while the amino acids are being synthesized. A process that takes, well, if you think that a single amino acid is synthesized every 4, you get 4 amino acids per second on average. You're talking about a process that lasts almost a minute, and you can actually simulate. So really, this can do a very, very, very drastic acceleration, getting you right into the biozone at the price of not knowing what you're doing. I'm putting this in the wrongest possible way. Of course, if you think you need a lot, if you wanted to be optimistic, and I think you should at some time, you need a lot of validation work to make sure that your assumptions actually hold and they are transferable. Meaning, I use this collective variable to study protein folding with this protein. I don't have to invent a brand new one for the next one, for the next protein. Probably it is transferable to all proteins, right? Otherwise, every protein would require its own algorithm. So, what I'm trying to say is that there are methods that serve specific purposes, and in some sense they are orthogonal. Now we, for the first time in the course, finally begin to give a meaning to the title of this course. There is alternative. Now, AI and machine learning is sort of trying to build a bridge between these. Trying to build methods that learn the collective variables possibly in an unsupervised way, and use this information to accelerate the dynamics. So you can think about it, if you want, in a exploration and exploitation ways. You use some of your simulations to learn the collective variable, and then that's the exploration, and then you exploit this collective variable to accelerate, and then you start again refining your collective variable, and then you accelerate. You see? So machine learning is really changing this paradigm. I would have stopped my lecture before the sentence, say 5 years ago, maybe 7 years ago. Nah, 5 is likely. It's more likely. Nowadays, really machine learning is putting some, is forcing us to reconsider this separation. So what should you use? Well, it depends on the problem you have, right? The problem with collective variables, which I used for a long time and I still use, and I built a company out of it, an enhanced sampling method based on a collective variable. So I'm not demising it in any form, is that you never have control on the error you're making. Because you don't know. It's like an evaluation, a calculation. If you don't know how good is your initial wave function, how can you trust your prediction? In contrast, you're probably familiar with perturbation theory, where you knew that you have a bound of the error that you're making. Right? Okay, so this is a first glance to the relevant problem. And what are we going to do is today I will very, 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 very briefly overview these two. And then we will take a look on this. And probably tell you one of these. Okay? I will not be thorough on this, because really much today in 2026, it really is better to first find a problem, identify what method you need, and then go deep on that method, rather than to survey them all, given that this is a very much landscape in motion because of AI and because of things are transformed. So I think it's important to give you a flavor of what these things do, rather than to go very much deep into any of them. Okay, so let me give you a couple of, today we'll just give you the example of replica exchange molecular dynamics. Replica exchange molecular dynamics is a way to sample the Boltzmann distribution and not the dynamics. So first of all, in replica exchange molecular dynamics, you really do not give any physical meaning to the trajectories. You only try to look at trajectories as ways of exploring sampling the Boltzmann distribution. So the way replica exchange molecular dynamics works is by running many replicas of the system. That means many MD trajectories in parallel, okay? But at different temperatures. Say this is the lowest temperature, is typically the temperature we really want to simulate the system. Say this is 300K, right? Now clearly, if you remember, the activation time decreases exponentially with the temperature, because it is the activation time scales with e to the delta u over kt. So if I increase temperature, I exponentially decrease this distance, this gap, right? So if I have a hot system, it thermalizes and crosses barrier much faster, because the kicks are larger, and I need fewer kicks to get to the top of a barrier. Okay? So what do? You take a high temperature where your exploration is fast enough for you to be ergodic. Maybe for under 50 Kelvin. I don't know, I'm throwing some number. Okay? And you run your trajectory. Now, this trajectory will have very tiny oscillations because it's a room temperature. This one will have wider oscillations because it is a hot temperature. You make nothing of this because at 450 Kelvin, actually you shouldn't even be able to run simulations in water because water should be boiled. But boiling is not something you see in your simulation. And so this is physically meaningless, clearly. This is what we want. But the idea is that you run many of them in a range of temperature from 450 to 300. The ones that are closer to 450 are hotter. The ones that are closer to the 300 are cooler. And they get more and more realistic. So, oops. Well, clearly the dynamics here is realistic, here is realistic. So what do? Every so often, I make a breaking point, and I choose stochastically if I want to swap these trajectories with an acceptance rejection criterion. So now, a trajectory that was a high temperature starts going at low temperature, and a trajectory that was going at low temperature starts going at high temperature. Right? And there is an acceptance rejection criterion that is very sensible. It has to do with basically to ensure that the lowest trajectory will eventually sample the detailed balance condition and sample the Boltzmann distribution. Okay? If you do this, eventually you will be able, after a sufficient number of swaps, to bring one trajectory that has explored a lot, because originally it was a large temperature, maybe has swapped a couple of times, and eventually has reached the low temperature phase, right? And so after a sufficient amount of time, you throw everything away except the trajectory you want, the one at the room temperature. This trajectory will have explored far more, in principle, than a trajectory that remains at 300 Kelvin all the time. And then you use that trajectory for sampling. What's the catch? Sounds like a fantastic idea. But you know, in physics, there is a very famous theorem. It's called the no free lunch theorem. There is no free lunch. The acceptance rejection criterion depends on the relative temperature. Now, you basically are always rejecting big swaps. And you're only accepting neighbor swaps because those are the only ones that have decent acceptance criteria. So to keep a decent acceptance criteria, you need to use a huge number of in parallel trajectories, because only using, say, 15, 20 trajectories in parallel, you can guarantee that the swapping doesn't be rejected all the time. Okay? And out of these gazillion of trajectories, you throw everything away except one. So it's not as efficient as it sounds because you still throw away, maybe if you have 100 trajectories, you throw away 99% of your work. So you must hope that the acceleration made up for this so that, see, of course it's not the same as simulating 100 times longer trajectory, because these trajectories you can run in parallel, so you can work on parallelization and broadcast the information only at the swapping time. so that you can do massively parallel computing. At the same time, it is clear that it is not perfectly efficient. And in fact, I'm not aware of any major conformational transitions or major problem that has been solved by RMD. I might be wrong. Maybe the authors or the practitioners of RMD will be able to contradict, which I would be very happy to know. So there could be situations I'm simply not aware. But as a matter of fact, it's not something you can simply plug and play and be sure that you solve the problem.
Why not? Why just take a single trajectory and not
because all the others are thermalized at a very large temperature, which is unphysical.
No, but I mean, if at a certain time step I take the one that is at 300 Kelvin, then I wait a bit, it will swap with another, and then I can take.
Yes, but after they swapped, the new trajectory that will come down will thermalize at 300 Kelvin, and the trajectory that is swapped will thermalize at the larger temperature. But at larger temperature, things happen that don't happen at room temperature. So you don't want to get information for high temperature molecular dynamics to study low temperature processes.
And it doesn't make sense to take at different time steps. They are not close, like.
You know, the thermalization time scales is very fast, fraction of picoseconds. So it's not that it takes a long time to thermalize to low temperature. It takes short time. So really, there's no way to make use of that. Okay. Last but not least, transition path sampling. Again, I'm after only the general idea. Transition path sampling has been developed by 3 scientists. 2 of them, I think, are mostly associated with it. Peter Bullhaus and Christoph Del Lago. And the idea of transition path sampling is very catchy. Remember, I gave you an expression for the probability of a path. Right? Now you can use this to do a Monte Carlo in path space. So transition path sampling is basically a process not to sample the Boltzmann distribution, but to sample the path density, the transition path time. So in other words, you have a reactant, you have a product, which you must provide. In this sense, they are not collective variables, but they are likely to be defined in terms of other parameters. What is the native state of a protein? Yeah, you will need some kind of definition, right? Probably the fraction native context will be your last word on how it is defined. So there will be some residual CV dependency in how you define the states, okay? But other than that, you don't alter the dynamics. So basically what you want to study is the ensemble of transition from R to P. So it's more a method for mechanistic insights into transitions, okay? So how do you do? Well, you build a Markov state, Markov chain Monte Carlo. You start from a seed trajectory, a trajectory that takes you from R to B, whatever it is. Doesn't need to be a physical one. But already, this is what they call throwing the first rope, like throwing a rope across 2 sides of a valley, right? It's far from trivial to get in a trajectory that gets you there in some cases. But suppose you can do, then typically what you do, you select a random point in this trajectory, a frame, and you can either, if it's a simulation that contains velocity, you can restart velocities, randomize them, or if it's a configuration non-zero dynamics, you can just start a new process from there. And this is called the shooting move. We generate a trajectory. After sometimes, a few things can happen. None of the trajectories has reached the reactant or product, and you have run out of your previously set amount of simulation time you're ready to spend for a single move. And then you throw everything away. You start fresh. Or one trajectory has reached the product, and also the other one has reached the project. Now, by the reversibility of the dynamics, you can think about this as a process of a thermal exploration that ultimately regressed to the product. This is not a transition path. It doesn't contribute to the path integral that we discussed, right? The third possibility is that one branch will go to positive and the other branch will go to the reactant. If the dynamics has velocities, you have to make sure that the two trajectories have velocities that are consistent to one another, so you can interpret this as a single process. So there you go, you have a new trajectory. Is it a good trajectory or is it a bad trajectory? Well, you don't know. You have to compute the acceptance probability. Now, in most cases, the acceptance probability is trivial. Okay? And therefore, you start from a trajectory T1, which is completely unphysical. You get a trajectory T2. Then, of course, this might be the new move might be rejected. You stay with T2. And then you keep on going. You get T3, and so on and so forth. And at some point, you go into the production, and you count these as a statistically independent trajectories. Okay? So what is the advantage of this? Does it make sense to you as an approach? The probability of acceptance, for instance, can be obtained from the probability we calculated in the path. Remember? We knew the probability of a path. So we can use that in the Metropolis acceptance and rejections. Okay? What is the advantage of this? Well, it's in principle huge, because you see, in normal molecular dynamics, I have a barrier, I have to state RMP, and I have to wait an exponentially long time doing things I really am not interested in. Because all of these thermal oscillation and unsuccessful attempts are uninteresting to me. What I'm interested in are these barrier crossing events. Well, the advantage of transition path sampling is it only focuses on this part. Because it basically corresponds to stuff from here and try to build objects that do this, right? So in principle, you avoid an exponentially large time of simulation. Uninteresting simulation. What's the price to pay? Well, on the one hand, the price to pay is that the theoretical maximum acceptance probability is 25%. You can prove it. So anyway, 1 times every 4th, you get a good trajectory at the most likely less than that. Okay? But most importantly, each of these trajectories must last for the time typical for a barrier crossing event. Right? Because you have to at least make it to the reactor and to the product. And for most systems of interest, barrier crossing events, say, for the same problems for which you have milliseconds long dynamics. Of course, if you're interested into just a small molecule changing conformations, then things are completely different, of course. But for the systems for which you really need a non-sampling, because otherwise you have no way to go in, a single trajectory is microseconds, which means that a single move in transition path sampling, a single Monte Carlo moves is likely days of molecular dynamics in a cluster to get one Monte Carlo move. And then, number one, you have to consider that only 1 in 4th would be a good move. So it's like multiplying by 4 the length of a simulation. And then that you have to collect a statistically significant set of trajectories. So you have to be ergodic in the space of trajectories. You may say, okay, I can use the central limit theorem, and the rule of thumb is after 10 I begin to make sense, because root of 10 is 3, that is already significantly less than 10, right? Maybe 20 trajectories. Okay, it's 20, that means 100 microsecond simulations. Oh, it's much less than milliseconds, right? Or tens of milliseconds. There is, and this is why I like this method very much, by the way. But there is another problem. Ergodicity in the trajectory space may be tricky. Let me give you an example. Say you want to study a process in 2D for simplicity. Here I have a reactant, here I have a product, here I have a barrier. Then I throw my first rope, and my first rope is going down this way, okay? Then I start a shooting move, and after a while I get a new trajectory. Then I start another shooting move, and I get another trajectory after a while. But the probability that from this initial condition I will get a trajectory that visits the other side is exponentially low. But really exponentially low now with an action, not with an energy. So the action contains many, many terms. It's a very, very large number. This is very unlikely. You may say, okay, no problem. Let me start with two trajectories. One that goes up and one that goes down, right? Yes, but you can do that only if you know that there are two trajectories. And this you can do because this is a two-dimensional term model. But all you do in a simulation, you have a way to see a folding, right? You see one folding trajectory, maybe you pulled off the amino acids, that's your starting trajectory, and you start perturbing on that, and eventually you get an ensemble of trajectories. Even if you spend a lot of money and time, you get an ensemble. How do you know that there isn't such a thing as an entirely new process that you simply haven't had access because you started off from the wrong condition? Okay? So there are problems with any of these methods. This doesn't mean that these methods aren't useful and aren't important. I will discuss Markov state model next time because it requires some theoretical background that links to the spectral decompositions that we discussed today and builds on them to build its own theoretical framework. Okay? So ci vediamo giovedì.